Hi all, welcome back to Cracking the Fang interviews. Today I'm going to be talking about Leetcode number 70, which is climbing stairs. And this question is very popular at Facebook, Salesforce, Amazon, and also Microsoft. I have seen this getting asked for regular software engineering and also data science slash AIML interviews. And let's start looking at the problem. I also have a link to the Leetcode problem in the description below. So the problem is asking us, is giving us a scenario where you are climbing a staircase and it takes n steps to reach the top. So you've been given n steps, and each time you climb one or two steps, that's the constraint. You can either take one step or you can take two steps and reach the top step. So the question is asking us how many distinct ways can we climb the top. So something I want to emphasize here would be the pattern that you observe. Whenever the question asks you to find how many distinct ways you climb to the top, or how many ways, this is a type of problem we typically solve with something like recursion. And of course, as we spoke in the previous video, the Fibonacci sequence video, you can always optimize a recursive program further using dynamic programming. All right, so let's look at an example of the problem. First, establish it. So we have been given n equal to 2. The way you can climb two steps. Let's just solve it by hand first. You can take one step and one step, so you'd have one way. Then you can take two steps at once and still reach the top step. So there are two ways of solving this problem. Now I'm gonna try with the other example I have here, which is n equal to 3. So you have a staircase with 3 steps. You take one step, one step, one step, that's one way. Then you take two steps and one step, or you take one step and two step. So this is the second way, this is the third way. So there are three ways of solving the problem. Now, the reason I mentioned recursion, whenever you're asked something which has to do with subproblems, for example, the number of in this case, the number of ways in which I can climb two steps clearly depends on can be broken down into the number of ways I can solve for one step and the number of ways in which I can solve for one step, because n equals 1 plus 1 equal to 2. So in this case, for one step I can solve it in one way. For one step I can solve it in one way. So in all, my answer would be 2. So this is clearly a recursion problem. You can break it down into individual subproblems. Same for 3. The way you'd break 3 is 2 and 1, or 1 and 2, and so on. And you'd still be able to solve for the entire problem. So as established, we'll be going with the recursion approach. The way we can break down this recursion problem is if you're given n equals 3, meaning 3 steps, and we're going to solve for that. What we could do here is further break down the problem by taking either one step or two step. So if we take one step, we make it n equals 2, and if we take two steps, we make the problem n equals 1. The way we could represent this in recursion is we could say, I'm going to call this recursive step. Recursive step for given n equals 3. You can break it down into recursive step n minus 1 and recursive step n minus 2, and use this expression, solve each of these subproblems as finding number of ways, add them, and further break it down, and so on. this is how the recursion tree will look like. And this is the most basic approach to solve the problem. And again, as if you haven't seen already, watch the previous video, which is the Fibonacci number video. It would give you the fundamental of calculating the time complexity of this approach. But in general, just to break it down, the generic way in which you can calculate the time complexity of a recursive algorithm is O of branches power depth. So in this case, the depth is the height, maximum height of the recursion, which is going to be, you'll start with 3, you'll go to 2, 1 and 0 all the way, where 0 is going to be your base case and 1 is also going to be your base case. And the number of branches you're taking is 1 and 2. So this is again an exponential time algorithm. We can further optimize this using dynamic programming. So if you were to quickly write code for the recursive approach, I'm going to say def recursion underscore climbing stairs, and send in the parameter n. As I said, the base case is going to be if n is less than equal to 0, equal to 1, you return n, because if you have 0 stairs, the only way you can do it, there's one way to solve for this, which is 0. You can't climb it given you the options you have is 1 or 2 jumps at once. And if you have 1 stair, n equals 1, the only way you can do that is essentially climb it one way. So the answer is 1. So we return 1, and the other, this is the base case. I'm writing pseudocode in Python, but the concept is pretty generic and you can apply it across any programming language. And else you'd return recursion climb stairs n-1 plus recursion climb stairs n-2. And as discussed in the previous slide, this is how the recursion tree would look like, and the time complexity will be 2 power n. The space complexity, again, time complexity will be 2 power n. The space complexity will be O of n. The reason for this is we'll have n number of call stacks that line up as we solve the problem, which is also the depth of the recursion. That makes the space complexity O of n, because every time you call, you're essentially making a new call stack before you get rid of this. So you're adding to the auxiliary space, which will be O of n. If I give you 5, you're going to call 4, 3, 2, 1, and so on. Now the question is, can we do better than exponential time? And as discussed in the previous Fibonacci number video, yes, we can do better using dynamic programming. And again, it's the same concept. This is the generic way in which you convert a recursive algorithm into a dynamic programming approach. This allows you to go from exponential runtime to polynomial runtime. And I'm going to quickly walk through the code. This is the code I've written on Leetcode. For base cases, for n equals 0 and 1, you have one way to solve it, as we discussed earlier. This is the regular program, and for the recursive steps, you can break it down in, for solving for n, you break it down for n-1 and n-2. And once you write the dynamic programming code, it's also called a memoized code. The word memoized comes from us using memory to store answers to subproblems. And again, what you essentially do is first store your base cases, and then you loop through the other cases, and you look at the previous 2 steps, the solutions, The way I come up with this expression is exactly the recursive expression. And once you're done looping, you'll be able to find the answer for a of n. And the reason we have n plus 1 here is in Python, for a for loop, it goes from the limit starts from 0 if you have 0 there, and goes till n minus 1. So it's up to but not including. So when we say n plus 1, it's gonna go to n. That's why we have n plus 1 here. And this way we convert something that is O of 2 power n exponential to O of n, which is polynomial. I hope this was helpful. Thank you for watching Cracking the Fang interviews again. Please like, share and subscribe to the channel for more